And so now it is my absurd pleasure to get to introduce our next speaker. I have been a fan of Kirk Johnson since I first met him when he was the chief curator at the Denver Museum of Nature and Science. An extraordinary thinker, a great scientist, and now he is the director of the Smithsonian Natural History Museum. And we are so fortunate to have him. So please take a deep breath, sit back in your chair, open your mind, and prepared to think about things differently. Please join me in welcoming Kirk Johnson.
Okay. The clicker's up on stage? Okay, perfect, thanks. Hello, everyone. You're probably wondering what a museum paleontologist is doing at a KOGA conference, but I just want you to remember that fossil fuels are fossils, so you are my people. And it turns out that I've always had a fair tie. I got my PhD in 1988 and actually went down and interviewed in the Gulf because the museum business wasn't looking so good then. And both of the fields have come up since then. And I've really traditionally always been a museum person with a strong sense of love of stratigraphy. So the image up on the screen right now is DMNS number 1. That's a well that was drilled and cored by the Denver Museum of Nature and Science in 1999. In the Denver Basin, and I think we still are the only natural history museum in the world that's drilled and cored a well. So the target was Denver Basin groundwater and understanding the geologic history of the Denver Basin, since we find so many amazing fossils in downtown Denver, things like a Tyrannosaurus rex skeleton in Littleton or a tropical rainforest in Castle Rock. So we use the same tools, we have the same vocabulary, we work in the same space, the same carapace of the Earth, the geologic layers that coat the Earth and are full of fossils and fossil fuels. And I consider myself to be sort of an exploration paleontologist, parallel to the exploration geologists. And you can see in this diagram that I've traveled to every time period in all continents in search of fossils. And my general premise is that all the good fossils are still on the ground, just as you would think about the fossil fuels. And we found amazing things in the last 20 years of my time in Denver, incredible fossil plants. Here's the most complete dinosaur ever found in North America that was found at the bottom of one of our excavations in Alberta. But in 2010, we hit the mother lode, sort of the equivalent of our unconventional play, in Snowmass Village, where excavation uncovered an Ice Age site that was truly phenomenal. And here's the moment of discovery: 3 construction workers, a bulldozer, and 3 mastodon tusks, ivory mastodon tusks. And we responded in force with a shovel army. My hero is Tom Sawyer. You know, the fence is really fun to paint, guys. It's really fun. And they emerged. And incredible bones. We collected over 6,000 bones in 70 days of excavation while moving 8,000 tons of dirt by hand with a team of 300 volunteers and staff. And acquired incredible treasures for Colorado, like this bison skull that's 6 foot 4 inches from horn tip to horn tip. Or this exquisite lower jaw, 3 foot long lower jaw of a mastodon. And this fauna, which was not known before, is now part of Colorado's lore. And here, when you go to Snowmass Village, you have to think about this is what Snowmass Village looked like 130,000 years ago. So what we're always doing in science is trying to discover new things, interpret them, and play them forward. And ultimately, the Earth's sedimentary carapace is vast and voluminous. You know that. That's what this amazing Bakken play is all about. And the best fossils remain to be found. So I'm always going to be on the search of getting teams out there discovering new things about the Earth. And it turns out there haven't been that many paleontologists for that long, and most of our insights are yet to come as we dig into the Earth's record. Now, I want to switch gears a little bit and talk to you about time in a different sense, because when people talk to paleontologists, their eyes often glaze over. I'm talking about 66 million years ago or 500 million years ago. You're thinking, I'm much more comfortable in 10-year increments or 5-year increments, as I heard earlier this morning, or 2-year increments. But I want to call your attention to this most extraordinary curve, which is the human population curve for the last 20,000 years, which is effectively flat for the first 19,000 years, and has made this miraculous bend in the last 1,000 years. And there's now 7.1 billion people on the planet. We just curved that number. Now, think about that. The last ice age ended about 12,000 years ago. We very quickly invented the ability to grow crops and to manage livestock, and very quickly after that we built the first cities. That happened about 10,000 years ago. But that didn't really affect the population curve at all. The population curve was affected because of the energy industry. It wasn't really until the use of coal and oil and other fossil fuels that we were able to dramatically increase the standard of living across the globe, which built larger cities and has created the modern world we live in today. So it's no small point to make that your industry is responsible for the state of the world today, which is an amazing thing. I mean, if you think about that, it went for many thousands of years with a major change, and then suddenly there's this tremendous growth of technology, population, and standard of living. Now, I take you to this picture I shot in 1997 in Mongolia. This is a 11-year-old Mongolian shepherd. And the thing about this shot is this shot could have been taken in 1200 AD. It could have been taken 1,000 years ago, because you can see the kid on his horse with a noose for a sheep and some yurts in the background. This could have been Genghis Khan's kid, but it isn't. It's a kid in 1997. And you realize that there are places in the earth where the industrial revolution has not yet caught up. So we have a long tail on population, people living in ways they've lived for a long time. And even in the first world, things only changed relatively recently. Here's an image of a guy named Bert. Bert was born in Sutton Veny in England in 1879, and he was a shepherd. He was just like that kid I showed you, except this is my grandfather. So my grandfather, born 1879 in England, was a shepherd, living pretty much as people have been living for 10,000 years until the world changed dramatically. So if you put some markers on here, there's Genghis Khan where the curve starts to bend, and there's my grandpa. When my grandpa was born, there was 1.7 billion people on the planet. And then my mom was born at 29, me at 60, and my nephew and niece last year at 12. So what's amazing to me about this curve is it's a very personal curve, as it will be to you as well. You all have grandparents that were born in the long time ago, and you have kids that are going to live to see the next century. So this curve is our curve. It's now, and it's our particular and interesting challenge. So it allows us to make statements that are quite extraordinary, like the 20th century is extraordinary when compared to the previous 2,000 centuries of our species' tenure on the planet. The first Homo sapiens appeared in Africa 200,000 years ago. And we get to live in the most interesting century. That's an amazing bit of good luck for all of us in the room. It turns out the next century is going to be really interesting too. So my point to you today, the take-home point, I'll come back to it again, is even though I'm a paleontologist, I'm really interested in the last 100 years and the next 100 years, which is what we're all talking about. Now, most of us have a hard time looking at more than 5, 10, sort of the maximum limit is your 30-year mortgage. And I want to stretch you to 100 years. And just for currency, I can claim ownership on the 20th century. I knew my grandfather. He was 21 years old when the century started, and I knew him. And I've seen 40% of it myself. So a century seems like a long time, but from the state of how long humans live and how families work, we all own this last century, the 20th century. And we're going to own the next century. I'll point to my friend Jack Harpole in the audience right there. Stand up, Jack. Give him a wave. Jack is going to be the Koga ambassador for the next century. He's going to be working on your 100-year plan because he's 11 years old right now, which means he has a pretty good chance of seeing the 22nd century. Wrap your brains on that one. So you look at something like the Denver Museum of Nature and Science, where I worked for a long time, an amazing place. It opened its doors in 1908. It seems like that's forever ago, but then this woman, Lucille Shaw, was living in Denver. She was 14 years old. That's my grandmother. She went to the opening of the museum. So it's just, a century isn't just that long. And what we heard about yesterday and today is how rapid technology changes and how fast we can jump on these changes. And we all know that the changes are happening really rapidly. So the paradox I present to you is, how do you plan for 100 years when you can't predict 4 years? That's your paradox. That's our paradox. It's our industry. And ultimately, your industry is the engine of civilization. That's very clear. That's why we are where we are. And how you perform and how you respond in the next century is critical to the future of humanity. So last year, I was plucked from Denver, and this is my new office on the mall. in Washington, D.C. And one of the things that's amazing, I had a foreign visitor from Europe visiting me. He said, you know, one of the interesting things about this country is you wrap your government in museums, which I think is a really interesting thing. I mean, museums are actually interesting places. They're places that preserve our culture for our culture. They're places that think in terms of long time strokes. They're forever places. We often say in the museum we're keeping these collections in perpetuity. What business plan do you have that goes in perpetuity? So there's some really long arc stuff in museums. And the National Museum of Natural History is the mothership of all natural history museums in the world. It's the world's largest natural history museum by far. Any way you want to count it. It's got an annual audience of 7.5 million visitors, which means that on any given day, for instance, the 4th of July, I saw 71,000 people in my building on one day, which is like dumping a stadium into a building and then dumping it back out again. And if you believe, as I do, that museums can impact people, which they do in a very curious way because they inspire people, they cause curiosity. They're not schools. They're places where you go and get inspired by stuff. And to have 7.5 million visitors flowing through every year, almost all unique visitors, almost all American tourists, or 15% are international tourists. What we're seeing is over a decade at this museum, we probably see on the order of 60 million people, roughly 18% of the nation's population, in the building being inspired about science. We also have 500 scientists and affiliated scholars, and we have the world's largest collection of natural history museum objects, 127 million objects. And the mission is pretty simple, understanding the natural world and our place in it, which is pretty much what we're talking about today. And just to give you a glimpse of the behind the scenes at the museum, it's a phenomenal place when you imagine storing 127 million objects. There are collections of all sorts of things, not just living organisms, but also objects of earth science and objects of human culture and anthropology. And this map shows the sampling density of where the stuff, the Smithsonian, comes from. And realize then that the Smithsonian really is not just the nation's museum, it's the world's museum. It's the largest museum in the world. And museums of a similar class, museums that are of size, there are less than 10 in the world. So natural history museums are relatively small at the large size category and amazing organizations. So what I want to do now is, given that background, that I'm a museum paleontologist and you're the Colorado Oil and Gas Association, which I must say is an incredible organization. I want to thank Tish Schuler for organizing this, but also Koga for being available to us. And over the years, while at the museum, George Sparks and I participated in Koga, and it's great to get a real perspective on the industry that's so near and dear. We've had great board members on the museum at Denver from Koga and others, and it's not an obvious match, but it's a natural match when you think about it. What I want to do now is take 5 examples from the last century about major innovations, how they happened, how people responded to them, and how they're part of what you take for granted as life as usual or business as usual today. Because these things map onto how we understand the world, and I can guarantee you, I mean, we're all amazed by this horizontal drilling, hydrologic fracking thing that's gone crazy. And I was just up in the Bakken last month looking at what's going on in North Dakota. It's an amazing innovation, but hold on to your shorts. The 21st century is going to be full of amazing innovations, and it's going to be an incredible place for people who are nimble and quick thinking to move our culture forward. So just 5 examples from the last century. I'm not going back millions of years ago. I'm going back in time only as long as my grandmother, grandfather, and my mom and dad have lived. And the first one is life on Earth. You're thinking, this is an oil and gas meeting. Well, remember that your oil and gas used to be life on Earth. It just got buried, squished, and cooked. But it's still life on Earth. And these are marine organisms that we've been collecting in the middle of the Pacific at a depth of 1,000 meters, a place that no one's explored before. We're lowering down trawls that don't squish the animals so we can bring the animals up intact. And there's a world of unknown species down there that we're finding on a regular basis. Here, beautifully photographed by Karen Osborne, one of our marine biologists. And we also have the world's largest collection of whales, over 150 whale skeletons. There's the lower jawbone of the largest blue whale ever collected. The jawbone is 25 feet long, weighs 1,000 pounds. But these are all part of this. And you inherently know the world is very rich in different kinds of species. These are the things that share the planet with us. And one of the things that really attracted me to the Smithsonian was this thing called EOL, the Encyclopedia of Life. And when I was interviewing for the job, they said, look, we have this ambitious goal to have a website that has a page for every species on the planet. And I said, there's 1.9 million species. How could you possibly do that? I said, well, we've actually got 1.1 million pages already. And as of last week, we're at 1.3 million pages. So imagine a reliable source for all of life on Earth. Now, we know that there's more life than we know about, but let's start with what we know about and get a wrap around that. And I want to take us back to this insight that's not that old. This is what I call Darwin's insight. And Darwin's insight, posited by Charles Darwin, was that, and it's a simple insight, all life is related to each other. That we're not from different origins, we're all related to each other. And it was heretical at its time, as you know. But as we've filled in the fossil record, we've realized that there are missing links everywhere. Here's just one image that shows the evolution of whales from terrestrial mammals. And then in 1953, there was an amazing discovery, the discovery of DNA, the double helix structure of the organic molecule, which all living things share. It was really the denouement of Darwin's insight. We are all related. We share DNA. And once we got DNA, we're able to start mapping how life is related. So now you can look at this crazy diagram, which is life on Earth. You can actually look in the upper left-hand corner, you can see humans, one of the 1.9 million species on the planet, which is an incredible thing to think about, that we have that big of a family. What happened in 2003 was pretty amazing. The National Institutes of Health, National Human Genome Research Institute completed a project where they sequenced the entire human genome. And from a technological point of view, think about this. The genome has 3 billion base pairs in it. You have to sort, measure, identify, and computerize 3 billion numbers. It was a 13-year project, took tens of millions of dollars to do it. It was actually $1 billion to do it. But they had then literally the blueprint for humanity. And we have been, National Institutes of Health is in Washington, D.C. We've been working with them, and the original sequence took 6 to 8 years, cost about $1 billion. The rate of technology in genomics is moving faster than technology in the oil field, I can guarantee you. They're piggybacking on Moore's Law. Right after the human genome, you could have done it in 3 or 4 months for $10 to $50 million. Today, if you want your own personal genome, $4,000, 3 days. They're pushing towards the $1,000 human genome probably in the next year. It is a phenomenal rate of understanding, and you may not know why it matters, but realize that this holds the key to personalized medicine, a real understanding of all sorts of biological questions we never thought we'd get to, and because of technology, we surged right to the finish line ahead of time. We just opened this exhibit in the museum called Genome, Unlocking Life's Code, and it's great for all of us because genomics has come up so fast. Like most technological developments, it catches most of us flat-footed. We're focused on what we're focused on. We miss the other big things that are happening in the world. And Peter Creever was talking about the Planetary Genome Project. We actually already have that. It's called the Global Genome Initiative. And if you remember those 137 million objects that we have in our collections, they're all of the different organisms on the planet. We actually have examples of nearly 1 million species in the building. And now with genomics, we can start mapping the genomics of all those species onto human genomics, which allows us to tackle problems like disease, genomic disease, food security, all sorts of issues that were once thought to be challenges that could not be met by humanity. Much as we thought we were running out of natural gas, we thought we couldn't grow enough food, there's some really amazing potentials when you start doing the science of biology. And words like this, synthetic biology, what's that? Creating organisms? De-extinction? Making an animal unextinct that's been extinct. Exobiology. I mean, we were all surprised in the Gulf spill how those microbes came to work for the spill. I mean, there's a lot of things going on that we're starting to understand now that the world has got all more kinds of life than we ever thought about. Or when we're drilling deep in wells, we're finding there are living organisms deep below the Earth's surface, and it's now pretty well accepted that the biomass of living things beneath the Earth's surface is greater than the biomass of things at the Earth's surface. Would have never predicted that 10 years ago. Second example is time. So we entered the last century not really know how to tell geologic time at all. This diagram wouldn't have had those numbers down the right-hand side in 1900. And in fact, that created an opening, and the rise of creationism in America started with this guy, George McCready Price, who realized that geology couldn't really say how fast things happened. So he made the argument, they don't know, it must be the biblical sequence. And he published this book called God's Two Books. One of the books being, of course, the Bible, the other one, of course, being the stratigraphic section. And he could actually make the argument pretty cogently because we couldn't put numbers on rocks. But then that story is told really well in this book called Rocks Don't Lie by Dave Montgomery, a geomorphologist at the University of Washington. But things were changing in science very rapidly. You know, the story of Marie Curie, who discovered radioactivity. And then this guy you may not have heard of, Arthur Holmes, who graduated from college in 1910. And his senior project was to do the first radiometric date of a Devonian rock, of a rock. And he dated a rock that was 370 million years old. He's like, hey, I can actually date the entire geologic timescale. And by 1913, remember this guy 3 years out of college, he had actually used radioactivity of helium and lead to make a calibrated geologic timescale and put time on the rocks. It's still a technique we use today. This guy's 3 years outside of college, and he drops time on Earth history. And here's his original, he kept working on it through his entire life, refining it and refining it. Here's his 1947 timescale against the timescale we use today, effectively. He's getting really close by himself by 1947, using just these little zircon crystals, which are in every one of your wells. They're 100 microns long. They're formed in magma chambers. They crystallize at the time the volcano erupts. You can take them. All you do is dissolve them, put them on a filament, run them through a mass spectrometer, sort the uranium lead ions from the lead ions, and measure the actual age of the rock. And it's quite simple to do. You go back to a lab at MIT. It's no harder than fracking a well, guys, I'm telling you. But through this technique, we now are the oldest rocks on the Earth are. We know how old the Earth is. And we can measure Earth events with tremendous precision, precision that has increased an order of magnitude in the last decade. It's amazing how all forms of science are surging forward. And one of my challenges to you is there is so much multidisciplinary opportunity out here if you can actually embed the breakthroughs in one field to the field that you're in. So back to that thing, now we've got numbers on the chart, which is great. Location. Life, time, location. This spot, we would have assumed that this spot hadn't moved, but it turns out that at the turn of this century, there was one crazy guy who everybody disbelieved who thought that the continents moved. This guy, Alfred Wegener, born the same year after my grandfather. So he seems like one of my relatives. And then this guy, Harry Hess, who taught at Princeton University, who was a Navy commander in World War II. And as he drove his transport ships back and forth across the Pacific, he took soundings and wrote them down. And he mapped the bottom of the Pacific over the course of World War II, took that data and posited plate tectonics. And when he posited it, people said, no, you're like that guy Alfred Wegener, and you're crazy. But by 1966, it was clear that he was right. So his model, the plate tectonic model, didn't receive major acceptance until I was 7 years old. How basic it is how we think about things today. And if you look at the map of the seafloor now, that's a heat-based map of the seafloor showing you the age of the rocks on the bottom of the oceans. So each one of these things allows us to get closer and closer to understanding how the Earth works, how we know what we know about the Earth. And of course, this is all deeply relevant to your business. One other thing that Harry Hess did that most people don't know is that he was the leader in the offshore drilling program. He was the first guy who wanted to drill a hole down to the Moho to test his own theory. And he led the way towards drilling holes at the bottom of the sea off ships, which of course led to some other developments. And I was pleasure just a couple of years ago went out and visited this platform Holly in the Santa Barbara Channel. This was put in the channel in 1963 when I was 3 years old, and it's still producing oil and gas today. So there's these innovations that start with smart scientists, then get leveraged by smart engineers. This is what makes this big wheel turn, what this big flywheel turn. Death, right? Life, time, location, death. Well, we think of death really in far too personal a way. We're worried about our own death and the death of our relatives. But there's another kind of death on the planet, that's the death of species, extinction. And we know from the fossil record that things go extinct. We didn't always know that. In fact, we didn't really figure it out until about 1840 that there were things that had been alive that are no longer alive. But once we realized that there are things that were alive that are no longer alive, we started asking the question, well, why do they go extinct? What causes extinctions? And in 1980, there was this very compelling but crazy idea put forth that the dinosaurs were killed by an asteroid. And everyone, myself included, I was 20 years old at the time, said, that's National Enquirer science. Can't possibly be. But the guy that proposed it, this guy, Walter Alvarez, born in 1940 at Berkeley, is one smart cat. And his dad, Louis Alvarez, was a Nobel-winning physicist who'd been part of the Manhattan Project during World War II and really understood isotopes. And what they found was a rare metal called iridium, which is extraordinarily rare on the surface of the Earth, but is quite abundant with other platinum group metals in asteroids. And they found this layer right at the level that marked the last dinosaurs. And their hypothesis has stood 33 years of testing, and it really is the standard accepted theory that, in fact, we have to worry a little bit about asteroids. And the big ones we have to worry a lot about, because it looked like in this impact, this thing racing in, the thing's about the size of Denver, about 6 miles in diameter, traveling at about 20 times the speed of a rifle bullet. This is what we call a hypervelocity impact. When it hit, and it hit in what is now the Gulf of Mexico, it punched a hole that was 20 miles deep and a mile wide. And then it quickly collapsed in, making a crater that was 180 kilometers wide, 2 miles deep. And it took oil company geologists using seismic to find it, because it's been buried in the 65 million years since it formed. But that event nearly toasted life on the planet. From what we can tell, the largest land animal to survive the event was about the size of a cat. So anything that was bigger than a cat was too exposed to the after effects and literally burned, suffocated, starved, or died, and you have a brand new world. So this world of the end of the Cretaceous, we never really thought much about why the dinosaurs went extinct, because we had no way of testing it, but we were presented with this crazy extraterrestrial hypothesis how to find this thing. The crater was found, but also the debris from this crater has been located in hundreds of deep soil drilling project holes. So we can now predict where to find it and go find the actual debris from the crater and map the crater to the debris layer, to the corpses of the fossils below it, and pretty compellingly argue that life on land and sea suffered a major extinction because of an extraterrestrial impact. Now, you don't have to think back very far. If you go back to the beginning of the Apollo project, there was a pervasive thought that asteroids didn't even hit the Earth. They hit the atmosphere and they broke up. They even didn't think that Barringer Crater in Arizona, that thing called Meteor Crater, they thought that was a volcano. So the realization that we could be whacked by asteroids is new to us. In fact, it happened after I graduated from college. But now you can go put your finger on that layer. This is a spot actually in North Dakota on the Cedar Creek anticline, not too far from about 10,000 wells. And there's a layer that's a centimeter thick that has chunks of Mexico that were blown from Mexico to North Dakota. And if you look below it, one friend sitting on the layer, one friend sitting on a skeleton of a dinosaur, and here's another dinosaur. You find abundant dinosaurs below this layer, but none above. And this is sort of a hard picture to take a look at, but you can see that there's two legs coming out at you. There's a rib cage. This is the dinosaur's lying on its side that was filleted by erosion. So if you take the whole thing out and flip it over, which we'll do right now, there it is. It's a complete Triceratops. That one's in the National Science Museum of Tokyo, which, as the National Museum of the United States, I'm thinking that I wish we had more dinosaurs staying in the United States. If there's any of you dinosaur patriots out there, come see me later. But think about this. We can now combine these things. So here's a site we have that's just 38 miles east of here in the Denver Basin, where we have volcanic ash layers bracketing the KT boundary layer. We can now combine the uranium-lead technology of dating with the impact layer and put numbers on the impact. So here we are at 66.08 million years, plus or minus 20,000 years. We can precisely time when that asteroid hit on the planet. Last one, climate. This one's been a little bit touchier lately. I know this because I did a 20-city tour for the American Association of Petroleum Geologists and did 20 lectures from Fairbanks to Louisiana and from Albany to San Bernardino talking about climate. And I'm not really sure why I accepted that task. I can assure you it was fascinating. And here's my history with climate. I started early in my field. I got very lucky early in my career and went 2 summers to the high Arctic, well above the Arctic Circle with National Geographic, to this place called Ellesmere Island, which still has polar ice caps on it, amazing ice caps. And it's just a huge place. Ellesmere Island is the size of England. It has 200 people living on it, mainly a couple of Inuit Indians and some Royal Canadian Mounted Police. It's next to an island called Axel Heiberg Island, which is the size of Ireland and is uninhabited. And here we are exploring that island. It's an amazing place because there is nothing between you and the geology. And we flew around by choppers, and what's amazing is there are huge, thick coal seams up there. And we found a coal seam that was 100 feet thick at latitude 84. 2,000 miles north of the nearest modern tree. And as we continue to look at these coal seams, we found that they are in fact were full of fossilized tree stumps and contained fossil forests. And we could take the fossil plants out and reconstruct what those forests looked like. One of the most amazing things was that we collected fossil animals, and instead of finding fossil polar bears, we found fossil crocodiles and turtles and snakes at latitude 84. And you might say, well, maybe that just drifted up there after they deposited, but we already solved that problem because you can use the paleomagnetics of the rock to tell where ancient continents were when. And in fact, that was a little bit further north, 50 million years ago. So you come to this conclusion that, wow, the world's climate just changed dramatically. Here's Ellesmere Island 50 million years ago. Here it is today. Big difference. And in 2004, there was a European-American drilling project where they went out into the middle of the Arctic Ocean, drilled the bottom of the Lomonosov Ridge, that long, narrow ridge that cuts across the Arctic Ocean basin, and they pulled up sediments that were 47 million years old, and much to their amazement, instead of finding marine microfossils, they found freshwater microfossils of a certain floating aquatic fern called a zola. Here's what it looks like in the Arctic Ocean today. Here's what that fern looks like, and here's a photograph I've taken of a lake in Amazonia that's covered by that floating fern. So in that warm world of the Eocene, that 50 million year old world, there was so much fresh water run off into the Arctic Ocean that there was a lens of fresh water sitting on the top, and there were floating aquatic ferns in the Arctic Ocean. It's a warm world. I'm not getting to go for it. There we go. So you start thinking about these discoveries, and then as the technology comes along, there's been a very aggressive scientific ocean drilling program that started with Harry Hess's idea and has continued through the deep sea drilling project, the ocean drilling project, and now the integrated ocean drilling project, which is 26 countries that drilled thousands of holes in the ocean floor to understand the ancient climate, ancient oceanography. You can see the density of holes they've drilled. And as you know, this kind of underpins offshore work. This is sort of the basic framework. And what we've come to realize is that the Earth has 2 predominant climate states. One of them, which you know about, called icehouse Earth. That's what we're in today, when there's a polar ice caps. And one of them, which is less well known, called greenhouse Earth. And during greenhouse Earth times, there's no ice at the poles at all. The poles are, in fact, forested. Evidence I just showed you. And the Earth has gone through this sequence twice in its history. There are 2 major periods of greenhouse and 2 major periods of icehouse. And this is over the last 600 million years. So it's a deep time thing. Don't worry about it. It happened 300 million years ago kind of question. But one of the insights from this is that when the carbon is in the atmosphere, you have greenhouse Earth. And when the carbon is in the ground, you have icehouse Earth. And we've been in icehouse conditions for the last 34 million years. And those blue bars show you when we're in icehouse. So the last 34 million years have been icehouse with polar ice caps. And then it turns out that in the icehouse world, you have these conditions where there's ice at the poles but not at mid-latitudes, and then you have times when the ice comes to mid-latitudes, called glacial periods. And the last one of those ended 15,000 years or so ago, and I'm from Seattle, and I like this image of the Space Needle up against the 3,000-foot thick layer of ice that would have been in Seattle 18,000 years ago. So one of the key points is the Earth is tremendously dynamic in climate terms. And you would say, well, that's fine because it's not going to happen in the next 100 years. So we bore in a little bit more, and people started realizing that you could actually core the ice caps, Greenland and Antarctica, amazingly challenging things. First time it was completed was 1966, Camp Liberty, or Camp Century on Greenland, where they cored nearly 5,000 feet of ice and got to the bottom. First people to core to the bottom of the ice sheet there. And then more recently, this incredible hole, the Epica hole at Dome C in Antarctica, where they cored a 10,400 foot hole in ice and brought back the climate record of the last 800,000 years. So remember, in all of these things, we're increasing our time resolution, our proxy resolution. We're getting better and better at understanding the past at finer and finer resolution. And then we also think about what's going on now. And this is Charles Keeling, who I like him because he was born a year before my mom and he died a year before my mom. So he's pretty much my mom and my little mental time break of where people are doing these things. And he started measuring the actual CO2 in the atmosphere at Mauna Loa in 1958 and created this incredible curve, which I'm sure you've seen. Just this spring, we crossed the 400 parts per million mark. Now, it's a big question for all of us is, at what point in adding CO2 to the atmosphere do you actually destabilize ice on the planet? At which point do you get back to the ice house greenhouse? We don't know the answer to that question. We would love to know the answer to that question, but one thing that's amazing is that that curve is my life. I was born in 1960, and the composition of the Earth's atmosphere has changed 20% since I was born. That's a really compelling fact in the mix. Add to that, with NASA and our ability to explore our solar system, and these are just a sample of the different kinds of satellites we have now looking out and in on the nature of the planet, the nature of information we have now is fundamentally different than it was 5 years ago. And we are in a time of exploding knowledge with attendant challenges. Think about the bioinformatics, the geoinformatics of just keeping all that data and tracking all that data. I was reading this morning about the first satellite images of the polar sea ice taken in 1966 were taken with a satellite but with film. And they had to lay out 40,000 photographs and stitch them together by hand to get the one image we can now just do in one flyover. So the potential is so fantastic. So these 5 things, my only point is that all that stuff, all that knowledge happened since my grandfather was 21 years old. And we didn't know any of it before it happened. So when we're talking about how amazing the horizontal drilling fracking thing is, I'm like, yeah, we expect to be surprised. Always expect to be surprised. Makes it difficult to plan, but that's the trend, right? So it leads us to this sort of situation where, in each case, new technology plus new insights dramatically opens new opportunities. We've been hearing about this for the last couple of days. Traditional camps are threatened, traditional views are abandoned, and we move forward. So where does that leave us now? Because what I'd like to challenge you to do is think about the next 100 years. I know it's tough to think about 5 years. So we just this really great panel where we heard that everything we predicted 5 years ago was dead wrong 180 degrees. So how can you possibly guess 5 years in advance? And here's some paleontologist asking for 100 years. Jack's going to be alive in 100 years. I know it. His vigor is there. Your children will be alive in 100 years. So it's really not as far away as it seems. And the plea really is, how do we work together? And I liked Kariva's talk a lot, is this is not an us against them, it's us on this planet. And what we need to do is work together to figure out where we want to be in 100 years, right? This whole thing about big vision is really important. The 100-year vision for the planet. I'm going to do a 100-year vision for the museum. Jack's going to do one for Koga. And ultimately, I think that we're in a really compelling time in human history. The next 100 years almost certainly is going to be more interesting than the last 100 years were. And they were really interesting. The next 100 years is going to play out in little 5-year bites. We're going to do our best to stick with those things. I'm going to do my job at the museum, the world's largest natural history museum, and try and inspire people to get excited about knowledge and innovation and thinking about the future. And I really love that we've got people like Schellenberger and Kariva here who are thinking, how do you imagine the future that we all want? The one where there's prosperity and happy, healthy families living sustainably and a natural world that's not degraded or depleted. And I can tell you we're going to have lots of really innovative tools to get there, but it's going to take real visionary thought from industries and politicians and individuals and kids, and it's going to take crowdsourcing and technology and everything we have. So I'm really honored to have spent 40 minutes with you guys. I think this is a really important thing you're doing, and thanks for civilization. Thanks.
All right, Jack, I need that plan by Friday at 5 p.m. So, pretty amazing, huh? Okay, you get a little networking break in the expo. Go hug an exhibitor, and then we will be back here at 1:15. We have two amazing keynotes, the chief economist for BP and David Ropeek on how risky is it really, risk communication. Look forward to seeing you there. Let's have another amazing round of applause